This is section 2.9. We're going to be looking at operations with complex numbers. First, we're going to take a look at graphs. When we graph imaginary numbers, the x-axis is the real axis, and the y-axis is the imaginary axis. Okay, so if we were going to graph a 2 minus 3i, we would go over to the right 2, just as we would for an x, and then down to 3i. Okay, so notice how the axis is labeled. The x-axis are the real numbers, the y-axis are the imaginary, so they have the i's. So if we were going to graph 2 minus 3i, it would be this point. So negative 1 plus 4i, we would go left 1 and up to 4i. 4 plus I, we would go to the right 4 and up to I. Negative I, we wouldn't go left or right any, we would just go down to I. Okay, here are a few more examples. What I'd like you to do is pause the video, graph each of these 4 points, and then hit play to check your answers. Okay, looking at absolute value of a real number, we should remember that it's the distance from 0 on the real axis. The real axis, which would also be a number line. The absolute value of an imaginary number is its distance from 0 along the imaginary axis. So here we have absolute value of complex numbers written out in words and in algebra and as an example. Okay, so the absolute value of a complex number, a plus bi, is the distance from the origin to the point AB in a complex plane, and is denoted absolute value a plus bi. Okay, the complex plane, that's the coordinate plane that we just graphed our examples on. Algebraically, we find the absolute value of this complex number by taking the square root of a squared plus b squared. Okay, now please remember that when we have addition or subtraction, the squares do not cancel the square root. So as we see in our example, if we want to find the absolute value of 3 plus 4i, square root 3 squared plus 4 squared, we actually square those two numbers, 9 plus 16, which simplifies to 5. Alright, find the absolute value of each, and what we're going to do is just use that equation where we have the square root of a squared plus b squared. So if we take a look at a, we're going to do the square root of 3 squared plus 5 squared. Okay, we actually want to square those, so it's going to be 9 plus 25. And the square root of 34, which does not have any perfect squares, so we cannot simplify it further. So that would be our answer. Alright, if we look at part B, negative 13, there is no imaginary number, so we could rewrite this as the absolute value of negative 13 plus 0i. Then set up our square root. We get the square root of 169, which is 13. Okay, for part C, notice there's no real part, so we could rewrite this as 0 plus negative 7i. Set up our square root. We get the square root of 49, which is 7. Okay, for our next example, we're going to look at adding and subtracting complex numbers. When we add complex numbers, what we do is add the real parts and then add the imaginary parts. So it's really just like combining like terms. When we add the real parts, we get negative 2. When we add the imaginary parts, we get negative 5. So we write our answer, negative 2 minus 5i. Okay, if we are subtracting we have to be careful to distribute the negative sign. So when we distribute, these double negatives become pluses. Then we do the same next step, where we add the real parts together and add the imaginary parts together. And then simplify, we get 7 plus I. We can also look at this using coordinate geometry. So we can add 3 minus I and 2 plus 3I by graphing. So the first thing that you want to do is graph those 2 points on the complex plane. So just like we started off with that complex plane, graphing those points, we're going to graph these 2 points and then connect each of these numbers to the origin with a line segment. Okay, so here's our complex plane. We're going to put those points in and connect them to the origin with a line segment. That's our first step. Alright, step 2, draw a parallelogram that has these 2 line segments as sides. Alright, so remember, a parallelogram has opposite sides that are parallel. So this side here, we're going to draw a parallel line right here from this point. And then from this line here, we're going to draw a parallel line up top. Okay, and the intersection of those points is the sum. So right here is 5 plus 2I, and there's our answer, 5 plus 2I. Alright, and if we check this answer just by simply adding like we did the previous examples, we add the real parts, we add the imaginary parts, we should get the same answer. Get the same answer because we're adding the same 2 parts, whether we do it algebraically or by graphing. We're also going to look at multiplying complex numbers. Okay, and an important fact to remember, I squared is equal to -1. Alright, so if we multiply -2I times the quantity 2 minus 4I, what we want to do first is distribute the -2I. So we get -4I plus 8I squared. Okay, and then remember that I squared is -1. So we get the answer -8 minus 4I. Okay, for our next one, now we have 2 binomial terms, so we need to distribute both the 3 and the 6I. Alright, so when we do that, we get 12 from 3 times 4, and then we have 6I times 4, which is where we got the 24I from. Then the 3 times -I gave us -3I, and then we had 6I times -I, which gave us the -6I squared. Okay, remember that I squared is -1. So when we simplify, this is actually going to become plus 6. So we can add that to the 12, and there's our final answer. Okay, our next one, multiplying these 2 numbers here, we multiply the numbers, we get -30, and then we get I squared. We know that I squared is -1, so our final answer would be 30. Okay, our last operation is dividing. So when we are simplifying with this, the I, remember, is the square root of -1. Okay, and we should remember from algebra that we cannot have a square root in the denominator. So what we need to do when we see an I in the denominator is multiply by the conjugate of the denominator. So if the denominator is 5i, the conjugate is -5i. When we multiply by the conjugate, we have to do the same thing to the top or the bottom. Inside these parentheses here simplifies to 1. So with our expression, we're multiplying our expression by 1, so we're not changing the value of our expression. It's a very, very important concept. Okay, we can't just multiply by 5i. We can't square it. We can't do anything that's going to change the original value. So if we multiply the top and bottom by the same thing, we're really multiplying by 1, so we're not changing the value. Okay, very important concept to understand. Okay, so now what we're going to do is distribute this -5i to the top and the bottom. Then remember our I squared here is -1. So -50 times -1 changes that to positive. And the next thing that we can do is to write this in our complex form, simplify it, and we get 2 minus 3/5 I. Okay, now when we simplify this, we can do -15i over 25 plus 50 over 25, okay, separating the denominator. So the 50 over 25 is where we got 2, and this -15i over 25 simplifies here. Okay, so just a little extra work shown there if we need it to simplify. Plus 8i over 4 minus 2i. So same idea where we have I in the denominator. Since I is the square root of -1, we can't have that in the denominator. So we're going to look at the denominator and multiply by the conjugate. The conjugate would be 4 plus 2i. So we're going to take our original expression, multiply by the conjugate. Okay, again, remember, top and bottom have to be the same. We're really multiplying by 1, so we're not changing the value of our expression. All right, now with our next step, distributing, we have a little bit of work to do. We have to distribute each of those numbers. So our 2 times 4 is 8. 2 times 2i is 4i. 8i times 4 is 32i. 8i times 2i, 16i squared. Now on the bottom, we left out a step here, just if we need it. 4 times 4 is 16, and then we have 4 times 2i, and then we have -2i times 4, and then -2i times 2i is here. So what happens to these middle terms, plus 8i minus 8i cancel out, which is why in this step we only have 16 minus 4i squared. All right, now we're going to simplify our I squareds we know are -1. Okay, so the 4i and 32i gave us 36i. 8 minus 16 gave us -8. 16 plus 4 gave us 20. And then what we can do is separate our denominator again. And then simplify.